Hello, and welcome to Sleep Archive. In the time that follows, we will explore the immense and intricate structure of the universe, moving from the familiar ground beneath us to the furthest reaches of the observable horizon. As you listen and rest, we will observe the quiet mechanics of gravity and the vast scales of space, beginning our journey with the most local of celestial arrangements. As we begin to look outward at the structure of the universe, it is helpful to start with the relationship between the Earth and its only natural satellite, the Moon. This arrangement is our most immediate experience of how matter and gravity interact in the vacuum of space. The Earth and the Moon are not merely two separate objects, but a bound system, locked in a stable gravitational embrace that has persisted for billions of years. When we consider the Earth, we often think of it as an isolated sphere, yet its physical reality is deeply influenced by the presence of the Moon. To understand the scale of this first step into the universe, one must first visualize the distance involved. The Moon orbits at an average distance of approximately 384,000 kilometers. In our daily lives, such a number is difficult to grasp, but it is a distance that could accommodate all the other planets in our solar system placed end to end, with room to spare. This space between the Earth and the Moon is not truly empty, but it is a profound vacuum, far thinner than any environment we experience on the surface of our world. The structure of this system is governed by the law of universal gravitation, which dictates that every mass exerts a pull on every other mass. The Earth, being significantly more massive than the Moon, exerts a powerful hold, keeping the Moon in a nearly circular, though slightly elliptical orbit. This orbit is a delicate balance between the Moon's forward momentum and the Earth's inward pull. If the Moon moved faster, it would drift away into the solar system. If it moved slower, gravity would draw it steadily inward. Because this balance is so precise, the Moon remains a constant companion. One of the most subtle and calming aspects of this relationship is tidal locking. Over vast stretches of geological time, the gravitational interaction between the two bodies has slowed the Moon's rotation until it perfectly matches its orbital period. Because of this, the Moon always shows the same face to the Earth. There is a quiet consistency to this arrangement. As the Moon travels around us, the same craters and ancient volcanic plains, known as Maria, are always oriented toward our planet. The far side of the Moon remains permanently turned away, a hidden landscape that serves as a reminder of the many layers of the universe that exist beyond our immediate sight. As you consider the Earth and Moon together, you may think about the influence they exert on one another. This influence is most visible in the rising and falling of the tides. The Moon's gravity pulls on the Earth's oceans, creating a bulge of water that follows the Moon's position in the sky. As the Earth rotates beneath this bulge, the water levels rise and fall in a rhythmic, predictable pattern. This is a physical manifestation of the invisible structure of gravity, a force that connects distant objects across the void. It is a slow and steady process, one that has occurred every day for billions of years, providing a reliable pulse to the natural world. Even the solid crust of the Earth experiences a subtle stretching and squeezing from these tidal forces, though it is far less noticeable than the movement of the water. The composition of the moon itself tells a story of the early structure of our immediate neighborhood. It is a world of silent grey dust and ancient rock, lacking an atmosphere to carry sound or weather. Without wind or rain to erode the surface, the history of the solar system is preserved there in the form of countless impact craters. Each crater represents a moment in the distant past when a fragment of rock or ice collided with the lunar surface. These features vary in scale from tiny pits to vast basins hundreds of kilometers wide. On the Earth, such history is often hidden by the movements of tectonic plates and the effects of the atmosphere, but on the Moon, the structure of the past remains visible and undisturbed. When looking from the Earth toward the Moon, we are also looking across a gradient of light and shadow. The phases of the Moon, from the thin sliver of a crescent to the full, illuminated disk, are simply a result of our changing perspective as the Moon orbits the Earth and is lit by the Sun from different angles. This cycle takes about 29.5 days to complete, a slow progression that has served as a primary clock for humanity throughout history. There is no urgency in this movement. It is a gradual transition that reflects the orderly nature of celestial mechanics. The space surrounding the Earth-Moon system is further structured by the Earth's magnetic field. This invisible shield, generated by the movement of molten iron in the Earth's core, extends far out into space, interacting with the stream of charged particles flowing from the Sunday. This region, known as the magnetosphere, creates a protective envelope around our world. The Moon, however, lacks such a field, leaving its surface exposed to the space environment. This contrast highlights the diversity of environments even within our most local structure. In the quiet of the Earth-Moon system, we find a microcosm of the entire universe. It is a place where gravity defines the paths of motion, where distance creates a sense of vastness, and where the passage of time is marked by steady, repetitive cycles. As we move our attention further out, away from the Earth and its Moon, the scales will begin to grow, but the fundamental principles remain the same. The bond between our world and its satellite is merely the first link in a much larger chain of structures that extend to the very edges of the observable horizon. For now, it is enough to acknowledge this local stability, the Earth spinning slowly on its axis and the Moon maintaining its silent, faithful orbit, together drifting through the immense dark as a single, coherent system. The stillness of the lunar surface, the rhythmic pull of the tides, and the vast, empty gap between these two spheres form the foundation of our understanding. We are anchored here, in a pocket of the universe that is familiar and well-ordered. As the mind rests on these images of orbiting spheres and the gentle pull of gravity, the complexity of the larger universe remains waiting, composed of the same silent forces and immense distances, organized in a way that is both intricate and profoundly calm. Leaving the Earth and Moon behind, we move our focus outward to the inner region of the solar system, a domain defined by 4 relatively small, rocky worlds that orbit in the warm light of the Sun. This area, often called the terrestrial inner circle, includes Mercury, Venus, the Earth, and Mars. Here, the structure of the universe is characterized by density and solid surfaces, a stark contrast to the vast gaseous expanses found further out. These 4 planets are the remnants of the early solar nebula's heavy materials, silicates and metals that could withstand the intense heat of the young sun. They sit within the inner gravitational well, moving at higher orbital velocities than the distant giants, tracing path after path through the vacuum with a steady, clockwork precision. Closest to the sun is Mercury, a world that exists in a state of extreme proximity to the solar furnace. Mercury's orbit is not a perfect circle but a distinct ellipse, bringing it as close as 46 million kilometers to the sun and moving as far as 70 million kilometers away. Because it is so deep within the sun's gravity, Mercury must travel incredibly fast to maintain its position, completing a full journey around the sun in just 88 Earth days. Despite this rapid transit, Mercury's rotation on its axis is slow and deliberate. It is locked in a 3-to-2 resonance, meaning it rotates 3 times for every 2 orbits it completes. This creates a strange and slow rhythm where a single day from one sunrise to the next actually lasts twice as long as its year. On the surface, the structure is one of ancient, airless desolation, much like our moon. It is a world of heavy iron, possessing a core that takes up a vast majority of its interior volume. This dense metal heart is a silent testament to the intense conditions of the inner solar system, where only the heaviest materials could congregate so close to the star. Moving outward from the sun, we encounter Venus, a planet often described as Earth's twin in terms of size and mass, yet its structural environment is profoundly different. Venus is shrouded in a thick, permanent layer of clouds that reflect much of the incoming sunlight, making it the brightest object in our night sky after the moon. Beneath these clouds, the atmosphere is incredibly dense, creating a pressure equivalent to being deep under a terrestrial ocean. This atmosphere acts as a thermal blanket, trapping heat and maintaining a surface temperature that is constant and searing, regardless of whether it is day or night. One of the most unique aspects of Venus is its rotation. It spins in the opposite direction of almost every other planet in the solar system. This retrograde motion is incredibly slow, taking 243 Earth days to complete a single rotation on its axis. There is a heavy, static quality to the Venusian landscape, a world of vast volcanic plains and highland plateaus where the air itself moves with the thickness of a fluid, governed by a slow, crushing equilibrium. Beyond Venus lies the Earth, which we have already touched upon, and then we reach the outer boundary of the inner circle, Mars. Mars is a smaller world, about half the diameter of Earth, and it marks the transition toward the colder reaches of the solar system. Its structure is one of rusted iron and frozen carbon dioxide, with a thin atmosphere that allows for clear views of its ancient geography. Mars possesses the largest volcanoes in the solar system and canyons that could stretch across entire continents, all of which are now silent and still. The planet's 2 tiny moons, Phobos and Deimos, are small, irregular fragments of rock that orbit close to the surface, likely captured asteroids that now follow predictable, rapid paths through the Martian sky. The distance between Earth and Mars is a shifting expanse, ranging from 55 million to over 400 million kilometers, depending on their positions in their respective orbits. This vast gap is a reminder of the increasing scale of the universe. Even between neighbors, the void is immense and quiet. The structure of the terrestrial inner circle is not just defined by the planets themselves, but by the light and energy that fill the space between them. The sun's gravity is the invisible hand that guides every motion here, while the solar wind, a stream of charged particles, constantly flows outward, washing over these rocky spheres. The inner solar system is a place of stability, where the orbits have been cleared of most debris over billions of years, leaving behind these four distinct worlds as the primary residence of the inner light. The sunlight takes only a few minutes to travel from the center to these planets, arriving as a steady, nourishing presence that defines the temperature and character of each world. As we visualize these four planets, Mercury, Venus, Earth, and Mars, we see them as a family of related structures, each with its own unique history and composition, yet all bound by the same physical laws. They spin at different rates and tilt at different angles, but they all participate in the same grand orbital dance. The inner circle is a compact and well-ordered region, a pocket of solidity in a universe that is largely composed of gas, plasma, and empty space. The rocky surfaces of these worlds provide a sense of permanence, a place where time is recorded in craters and canyons, and where the structure of the universe feels tangible and firm. As we drift further away from the sun, the warmth begins to fade, and the distances between objects begin to stretch significantly. The terrestrial inner circle serves as our home base, a familiar arrangement of stone and metal that prepares us for the much larger and more ethereal structures that lie ahead in the deep cold of the outer system. The transitions are never sudden. The universe expands its scale gradually, allowing the mind to adjust to the increasing silence and the thinning of matter as we move toward the edge of the sun's immediate family. As we move beyond the orbit of Mars, we enter a vast and transitional space that marks the boundary between the rocky inner worlds and the gargantuan gas giants of the outer solar system. This region is known as the main asteroid belt, a sprawling collection of millions of rocky fragments and icy bodies that orbit the sun in a wide, flat ring. Contrary to popular depictions that suggest a dense and crowded field of debris, the asteroid belt is characterized primarily by its immense emptiness. The average distance between any two asteroids is often measured in millions of kilometers, creating a quiet and lonely expanse where individual objects drift for eons without ever encountering another. The structure of this region is a record of the solar system's violent beginnings, representing material that was never able to coalesce into a full-sized planet due to the immense gravitational influence of nearby Jupiter. At the heart of this region is Ceres, the largest object in the belt and the only one classified as a dwarf planet. Ceres is a world of its own, possessing enough mass for its own gravity to pull it into a nearly spherical shape, measuring about 940 kilometers in diameter. It contains roughly 1/3 of the total mass of the entire asteroid belt, serving as a silent anchor in this sea of smaller fragments. As we consider Ceres, we see a world of water ice and carbonate minerals, suggesting a complex internal structure that may even harbor a subsurface layer of briny liquid. Surrounding Ceres are countless other bodies of varying sizes, from Vesta and Pallas, which are large enough to be considered protoplanets, down to tiny grains of dust that are barely visible against the blackness. These objects are categorized by their composition, reflecting the different conditions present in the early solar nebula. C-type or carbonaceous asteroids are the most common, appearing dark and ancient, containing some of the most primitive materials in the solar system. S-type or silicious asteroids are composed of stone and iron, while the rarer M-type asteroids are dominated by nickel and metal. The distribution of these materials is not random. It follows a subtle gradient that reveals how temperature and chemistry shifted as the solar system took its form. The organization of the belt is further refined by a phenomenon known as orbital resonance. Because Jupiter is so massive and orbits just beyond the belt, its gravity exerts a rhythmic pull on the asteroids, creating gaps in their distribution. These areas, known as Kirkwood gaps, are regions where the orbital periods would be a simple fraction of Jupiter's own orbit, such as 3:1 or 2:1. Over millions of years, any object that entered these resonant zones was gently nudged into a different path, leaving behind a structured pattern of occupied and empty lanes. This gravitational architecture is invisible to the eye, yet it dictates the movement of every fragment of rock within the belt, ensuring a stable and predictable flow of matter. As you visualize this region, imagine the slow, steady progression of these millions of objects, each following its own elliptical path around the distant Sunday. There is no chaos here, only the quiet persistence of orbital mechanics. The sunlight in the asteroid belt is significantly weaker than it is on Earth, appearing as a bright, cold point of light that provides little warmth to these frozen surfaces. In the stillness of this region, the passage of time is marked only by the slow rotation of the asteroids and the gradual shifting of their positions relative to the planets. The belt serves as a storage vault for the building blocks of the solar system, preserving the chemistry of the distant past in a state of deep freeze. It is a place of transition, where the density of the inner system begins to give way to the vast, open voids of the outer reaches. The boundary of the belt is not a sharp line, but a thinning of material, a gradual decrease in the number of rocky bodies as we move toward the domain of the giants. The existence of the asteroid belt reminds us that the structure of the universe is defined as much by what did not happen as by what did. Here, the formation of a planet was interrupted, leaving behind a belt of leftovers that continue to follow their ancient, lonely cycles. There is a profound sense of scale in this region, as we realize that even a collection of millions of objects can still result in a space that is almost entirely empty. As we drift further outward, leaving the rocky fragments behind, we begin to feel the increasing pull of the most massive resident of our solar neighborhood. The transition from the asteroid belt to the outer solar system is marked by a dramatic change in scale and composition. We are moving away from the world of solids and stone, entering a realm where gas, gravity, and immense pressure define the structure of the universe. The quiet of the belt prepares us for the majesty of the gas giants, where the forces of nature operate on a level that dwarfs everything we have encountered so far. For now, we simply observe the slow drift of the asteroids, recognizing them as a vital part of the cosmic architecture, a bridge between the inner warmth and the outer cold. The stability of their orbits and the precision of the gravitational resonances provide a sense of order that persists even in the most remote parts of our solar system. The structure remains coherent, balanced, and remarkably calm as we continue our journey into the deepening dark. Moving beyond the threshold of the asteroid belt, the scale of the solar system undergoes a monumental shift as we enter the realm of the gas giants. The first and most imposing of these structures is Jupiter, a world of such immense proportions that it contains more than twice the mass of all the other planets combined. Jupiter is not a solid object in the way we understand the Earth to be, but rather a colossal sphere of hydrogen and helium, held together by its own formidable gravity. As we approach this giant, we see a world defined by horizontal bands of clouds, ammonia, ice, and hydrosulfide crystals that are stretched into long, colorful stripes by the planet's rapid rotation. Jupiter completes a full turn on its axis in less than 10 hours, a dizzying speed that creates powerful atmospheric currents and jet streams that have persisted for centuries. The structure of Jupiter's atmosphere is one of fluid dynamics on a planetary scale, where vast storms larger than the Earth, such as the Great Red Spot, churn with a slow and ancient energy. Deep beneath these visible clouds, the pressure increases to levels that defy our terrestrial experience, eventually compressing hydrogen into a rare state known as liquid metallic hydrogen. In this state, hydrogen acts as an electrical conductor, and its movement generates a magnetic field of incredible strength, far surpassing that of any other planet in our system. This magnetosphere extends millions of kilometers into space, creating a structured environment of radiation and charged particles that surrounds the giant. Jupiter is also the center of its own miniature system, possessing at least 95 moons that orbit in a complex web of gravitational interactions. The four largest of these, Io, Europa, Ganymede, and Callisto, each represent a distinct structural world, from the volcanic activity of Io to the icy subsurface oceans of Europa. As we drift further into the outer system, the distance between Jupiter and the next giant, Saturn, stretches across nearly 650 million kilometers of empty space. Saturn is the second largest planet, and while it shares a similar composition of hydrogen and helium with Jupiter, its structure is characterized by a lower density and its magnificent ring system. Saturn is the only planet in the solar system that is less dense than water, a fact that highlights the ethereal nature of these gas-dominated structures. The most striking feature of Saturn is, of course, the rings, a vast flat disk of ice and rock fragments that extends 280,000 kilometers from the planet's center. Despite their immense width, the rings are remarkably thin, often no more than 10 to 100 meters thick in most places. The structure of the rings is maintained by a delicate balance of gravity and orbital motion, with small shepherd moons clearing gaps and creating sharp edges within the icy debris. The rings are divided into several distinct sections, known by letters, with the Cassini division being the most prominent gap visible from a distance. Like Jupiter, Saturn is home to a vast family of moons, including Titan, the only moon in the solar system with a substantial atmosphere and liquid lakes of methane on its surface. The relationship between Saturn and its rings, and between the planet and its many satellites, is a masterclass in the organization of matter through gravitational resonance. In this region of the universe, the Sun appears smaller and its light is significantly dimmer, yet the gas giants stand as beacons of order and complexity in the cold dark. The structure of these worlds is one of layers, from the outermost wisps of gas to the crushing depths of the metallic interior, and finally to a small, heavy core of rock and ice. There is a profound stillness in the way these giants move, their immense mass lending them a sense of permanence and inevitability as they trace their long orbits around the Sun. Jupiter and Saturn act as the guardians of the solar system, their gravity influencing the paths of comets and asteroids, often shielding the inner planets from potential impacts. As you visualize these two spheres, one striped with storms, the other crowned with rings, you can feel the shift in the universe's architecture toward the massive and the fluid. The terrestrial rocks of our home are now far behind us, replaced by the majestic, swirling gases of the outer reaches. This part of the solar system is a place where gravity is the ultimate architect, carving out spheres of unimaginable size and ordering trillions of ice particles into perfect, translucent rings. The movement of these worlds is slow, rhythmic, and entirely unhurried, reflecting the deep time of the cosmos. As we prepare to move even further out, toward the ice giants at the very edge of the Sun's primary family, we carry with us the image of these two giants. They remain steady and silent, rotating in the cold vacuum, their presence a vital and stabilizing chapter in the long story of the universe's structure. The light of the distant sun glints off the ice of Saturn's rings and the tops of Jupiter's clouds, a quiet reminder of the connections that bind even the largest structures to the center of our system. The journey continues outward into regions where the cold deepens and the structure of the universe becomes even more mysterious and vast. Beyond the orbits of the gas giants, we transition into a region of the solar system where the temperatures drop low enough for volatile compounds like water, ammonia, and methane to exist as solid ices. This is the domain of the ice giants, Uranus and Neptune, two worlds that represent a distinct structural category from the hydrogen-dominated giants we have just left behind. Uranus, the seventh planet from the Sun, is a pale, cyan-colored sphere that sits nearly 3 billion kilometers away from the solar center. Its most striking structural characteristic is its extreme axial tilt, which is nearly 98 degrees relative to the plane of its orbit. This means that Uranus essentially rolls around the Sun on its side, leading to seasonal patterns that are unlike any other world in our system. Each pole of Uranus experiences 42 years of continuous sunlight, followed by 42 years of total darkness, creating a slow and rhythmic cycle of light and shadow that spans decades. The atmosphere of Uranus is relatively featureless to the eye, composed of hydrogen and helium with a significant amount of methane, which absorbs red light and gives the planet its soft blue-green hue. Beneath this atmosphere lies a vast, slushy mantle of water and ammonia ices, surrounding a small, rocky core. Despite its distance, Uranus possesses a delicate system of narrow, dark rings and a family of 27 known moons, all following the planet's unique, tilted orientation. As we move even further into the deep cold, we encounter Neptune, the most distant of the major planets, located 4.5 billion kilometers from the Sun. Neptune is a world of deep, vivid blue, possessing a more active atmosphere than Uranus, with high-altitude clouds of methane ice and some of the fastest winds recorded in the solar system. The structure of Neptune is very similar to its neighbor, consisting of an icy mantle and a rocky center, yet it radiates more internal heat than Uranus, contributing to its more dynamic weather patterns. Neptune's largest moon, Triton, is a fascinating structural anomaly. It orbits the planet in a direction opposite to Neptune's rotation, suggesting it was once a free-roaming object captured from the space beyond. Triton is a frozen world with geysers of nitrogen gas, representing the kind of material that exists at the very fringe of the Sun's planetary influence. As we leave Neptune behind, the structure of the solar system changes from large, isolated spheres to a vast, disk-like region of frozen debris known as the Kuiper Belt. The Kuiper Belt begins just past the orbit of Neptune and extends to about 55 astronomical units from the Sun, containing millions of icy objects that are remnants from the solar system's formation. This region is the home of the dwarf planets, including Pluto, Eris, Haumea, and Makemake, each of which follows a long, slow path through the outer darkness. Pluto, the most famous resident of this belt, is a complex world of nitrogen, ice plains, and mountains of water ice, possessing a large moon, Charon, with which it is tidally locked. The structure of the Kuiper Belt is shaped by its relationship with Neptune. Many objects are held in orbital resonances that prevent them from drifting away or falling inward. The space within the Kuiper Belt is incredibly vast and quiet, with objects so far apart that the Sun appears as nothing more than an exceptionally bright star. This region acts as a reservoir for short-period comets, those icy wanderers that occasionally journey into the inner solar system before returning to their home in the cold. As you visualize the Kuiper Belt, imagine a wide, flat ring of billions of frozen fragments, each one a silent witness to the earliest days of our cosmic neighborhood. The light here is dim, and the movement of matter is slow, taking centuries for a single object to complete a journey around the Sun. The Kuiper Belt provides a sense of the solar system's true scale, revealing that the planets are only a small part of a much larger and more diffused structure. The transition from the solid worlds of the inner system to the gas giants, and finally to this icy fringe, is a progression toward lower density and greater distance. In this outermost layer of the planetary disk, the influence of the Sun is still present, but it is faint, guiding these frozen bodies with a gentle gravitational hand. The structure of the universe at this scale is one of profound isolation, where individual worlds and fragments of ice drift through a vacuum that feels nearly absolute. Yet, even here, there is order and predictability, a continuation of the same physical laws that govern the fall of a leaf on Earth or the tides of the Moon. The cold of the Kuiper Belt is a peaceful, unchanging environment, a place where time seems to stand still as the centuries pass in silence. As we look toward the even more distant reaches that lie ahead, we see that the Kuiper Belt is merely the inner edge of a much larger envelope that surrounds our system. The journey into the structure of the universe is a journey of expanding horizons, where each new layer reveals a broader context for our own existence. For now, we rest our attention on the quiet, frozen architecture of the ice giants and the belt of ice, acknowledging the beauty in this distant, dimly lit corner of our home. The stability of these outer reaches provides a final, calming boundary to the solar system we know, preparing us for the transition into the truly interstellar voids that lie beyond. As we move beyond the outer rim of the Kuiper Belt, we begin to leave the flat, disk-like structure of the planetary orbits and enter the true frontier of the Sun's influence. This region is marked by two distinct and invisible boundaries that define the physical limits of our solar neighborhood. The first of these is the heliopause, the point where the solar wind, the constant stream of charged particles from the Sun, is finally slowed and pushed back by the pressure of the interstellar medium. The space within this boundary, known as the heliosphere, is like a giant magnetic bubble that protects the planets from the high-energy cosmic radiation of deep space. At the heliopause, the environment changes from one dominated by the sun's plasma to one dominated by the thin gas and dust of the space between stars. This transition is quiet and gradual, yet it marks a profound shift in the structure of the universe as we leave our home environment and enter the vastness of the galaxy. Beyond the heliopause, stretching thousands of times further than the planets we have visited, lies the most distant part of our system, the Oort cloud. Unlike the Kuiper belt, which is a flat ring, the Oort cloud is theorized to be a gargantuan, spherical shell of icy debris that completely surrounds the Sun and all its planets. It is the largest structure associated with our star, extending perhaps halfway to the nearest neighboring star, Alpha Centauri. The objects within the Oort cloud are incredibly far apart and very small, consisting mostly of frozen water, methane, and ammonia. These are the long-period comets, ancient travelers that take tens of thousands of years to complete a single orbit around the Sun. The structure of the Oort cloud is so vast that the Sun's gravity is extremely weak here, barely holding on to these icy fragments. Occasionally, the gravity of a passing star or the general pull of the Milky Way galaxy can nudge one of these objects, sending it on a long, slow fall toward the inner solar system. As you visualize this spherical shell, imagine billions of icy mountains drifting in near total darkness, spaced so far apart that you could travel for a lifetime and never see one. The light from the Sun here is indistinguishable from the other stars in the sky, a tiny, bright point of light that provides no warmth, only a faint gravitational anchor. The Oort cloud represents the outer envelope of our system, a quiet, frozen reservoir that marks the transition into the interstellar medium. The structure here is one of extreme diffusion, where matter is so sparse that it barely exists at all. Yet, this shell is a vital part of the cosmic architecture, defining the volume of space where our Sun is the primary influence. The distance from the Sun to the outer edge of the Oort cloud is estimated to be around 100,000 astronomical units, or nearly 2 light years. To cross this distance at the speed of the fastest spacecraft ever built would take tens of thousands of years. There is a deep sense of stillness in this region, a place where the frenetic energy of the inner planets has faded into a slow, glacial rhythm. The Oort cloud is a reminder that the universe is mostly empty space, and that even the most solid structures are surrounded by immense oceans of nothingness. As we look outward from the edge of the cloud, we no longer see the familiar arrangement of our solar system, but the vast, glowing sea of stars that makes up the Milky Way. The structure of the universe is now shifting from the scale of a single star to the scale of a galaxy, where the distances are measured in light years and the players are no longer planets, but entire stellar systems. The transition is seamless as the Oort cloud merges into the local interstellar cloud, a thin veil of gas that our solar system is currently drifting through. In this quiet, remote region, we find the ultimate limit of our home, a border defined by ice and gravity that sits at the edge of the great interstellar void. The structure remains orderly, even at this extreme scale, following the same laws of physics that govern the motion of the Earth and the Moon. The emptiness of the Oort cloud is not a void of meaning, but a space of potential, a giant warehouse of the materials that built our world. As we drift past the final, lonely fragments of ice at the edge of the cloud, we leave the Sun's family behind and begin our journey into the space between the stars. The silence here is profound, a deep and enduring calm that has persisted for billions of years and will continue for billions more. We are moving into the heart of the galaxy, where the structure of the universe reveals itself in the distribution of stars, the flow of nebulae, and the great rotation of the galactic disk. But for now, we linger at the edge, acknowledging the vast, spherical embrace of the Oort cloud, the final, quiet sentinel of our solar neighborhood. Leaving the Oort cloud behind, we fully cross the threshold into interstellar space, the vast and silent territory that exists between the stars. The structure of the universe at this scale is no longer defined by the orbits of planets around a single sun, but by the distribution of star systems within the local reaches of our galaxy. This region is often referred to as the local interstellar neighborhood, a volume of space stretching roughly 30 light-years in every direction from our sun. To visualize this, one must first adjust to a new sense of distance. While the planets are separated by millions of kilometers, the stars are separated by trillions. A light year, the distance light travels in a single year, is approximately 9.5 trillion kilometers, and it is the standard unit of measurement for this immense architecture. Despite the appearance of total emptiness, the space between stars is filled with the interstellar medium, an extremely thin mixture of gas and microscopic dust. In our local neighborhood, we are currently drifting through a structure called the local interstellar cloud, a slightly denser region of gas about 30 light-years across. The structure of this neighborhood is anchored by our nearest neighbors, beginning with the Alpha Centauri system, located about 4.37 light-years away. Alpha Centauri is not a single star but a triple system, consisting of a closely orbiting pair similar to our Sun and a much smaller, cooler red dwarf called Proxima Centauri. These three stars are bound together by gravity, performing a complex and slow orbital dance that has lasted for billions of years. Moving slightly further out, at a distance of about 6 light-years, we find Barnard's star, a dim red dwarf that possesses the highest proper motion of any known star, appearing to drift across the sky faster than its peers. The local neighborhood is populated by a variety of star types, though the most common are red dwarfs, cool, long-lived stars that are much smaller and dimmer than our Sun. There are also brighter, more massive residents, such as Sirius, the dog star, which is the brightest star in our night sky and located about 8.6 light-years away. Sirius is a binary system consisting of a brilliant white star and a tiny, incredibly dense companion known as a white dwarf. The structure of this neighborhood is not static. Every star, including our Sun, is in constant motion, orbiting the center of the Milky Way at speeds of hundreds of kilometers per second. Because the distances are so great, this movement is imperceptible to us over a human lifetime. But over millions of years, the arrangement of our neighbors shifts and changes. Stars that are close to us now will eventually drift away, and new stars will move into our local sphere, creating a slow and ever-evolving cosmic map. In the quiet of the interstellar void, the environment is one of extreme low density, with perhaps only a few atoms of hydrogen per cubic centimeter. This thin gas is occasionally enriched by the remnants of dying stars, which cast off their outer layers and seed the neighborhood with heavier elements like carbon and oxygen. There is a profound sense of peace in this region, a place where the local influences of individual stars are balanced by the overarching gravity of the galaxy. As you visualize this neighborhood, imagine a vast dark ocean where the stars are like distant, glowing buoys separated by leagues of calm, empty water. The light from these stars takes years to reach one another, ensuring that every observation we make is a look back into the recent past. The structure here is one of isolation and yet connection, as the invisible threads of gravity and the shared medium of the interstellar gas bind these systems together. The local neighborhood serves as our immediate context within the much larger disk of the Milky Way, a small pocket of stability within the spiral arms. As we look beyond these nearby stars, the structure of the universe begins to reveal itself on an even grander scale, where stars are counted in the hundreds of billions. But for now, it is enough to acknowledge the quiet company of our nearest neighbors, drifting with us through the local cloud in a steady and predictable journey. The stillness of interstellar space is not a lack of activity, but an activity so vast and slow that it feels like silence. The architecture of this neighborhood provides a sense of the immense scale of the galaxy, preparing us for the transition from individual stars to the great stellar sea of the Milky Way. Every star we see is a world unto itself, a center of its own system, yet here they are merely points of light in a much larger and more profound arrangement. The journey continues outward, moving from the local and the familiar toward the heart of the galactic structure, where the density of light and matter begins to rise once more. We rest in the knowledge that even in the vast gaps between the stars, the universe remains a structured and coherent whole, governed by the same laws that keep the Earth in its place. The local neighborhood is our porch onto the galaxy, a quiet space from which we can observe the grand rotation of the celestial spheres. As we expand our perspective further, the individual stars of our neighborhood begin to blend into a much larger and more complex architecture known as the Milky Way galaxy. This is the stellar sea in which our sun is but a single drop, a vast, rotating disk of stars, gas, and dust that spans approximately 100,000 light-years from edge to edge. The structure of the Milky Way is that of a barred spiral galaxy, characterized by a central bar-shaped region of stars surrounded by a flat disk with winding spiral arms. To visualize our position within this immense system, imagine the galaxy as a great, luminous whirlpool, with our solar system located about 27,000 light-years from the center. We reside in a smaller, secondary structure called the Orion Cygnus Arm, situated between two of the galaxy's major spiral arms, the Perseus Arm and the Sagittarius Arm. The spiral arms are not solid structures, but rather regions of higher density where gas and dust are compressed, triggering the birth of new stars. These arms glow with the light of millions of young, hot blue stars, creating a brilliant pattern that defines the visual structure of the galactic disk. Between these arms, the density of stars is lower, creating a rhythm of light and shadow as one moves through the galactic sea. The disk itself is remarkably thin compared to its width, appearing like a cosmic pancake with a thickness of only about 1,000 light-years in most places. As we look across this disk, we encounter a staggering diversity of stellar structures, from massive, short-lived supergiants to the tiny, ancient red dwarfs that make up the majority of the population. The Milky Way contains an estimated 100 to 400 billion stars, each moving in its own orbit around the galactic center, yet all participating in a collective rotation. Our Sun, for instance, travels at a speed of about 828,000 kilometers per hour. Yet even at this incredible pace, it takes about 230 million years to complete a single galactic year. The structure of the galaxy is also defined by the interstellar medium that fills the gaps between the stars, appearing as dark, silhouetted clouds of dust and glowing nebulae of gas. These nebulae, such as the famous Orion Nebula, are the nurseries of the galaxy, where the gravity of the galactic disk pulls material together until it ignites with nuclear fusion. In other regions, we see the remnants of stars that have reached the end of their lives, casting their elements back into the stellar sea to be recycled into future generations of worlds. There is a profound sense of continuity in this process, a slow and steady transformation of matter that has been occurring for over 13 billion years. The Milky Way is not a static object, but a living, breathing system of energy and matter, held together by the invisible threads of its own gravity. Beyond the stars and gas we can see, the galaxy is also structured by a vast amount of dark matter, an invisible substance that provides the additional gravitational pull needed to keep the outer stars from flying away. This dark matter forms a massive halo that surrounds the entire visible galaxy, extending far beyond the furthest stars. The atmosphere of the stellar sea is one of immense, quiet power, where the collective light of billions of suns creates a soft, ethereal glow that we see as the Milky Way in our night sky. As you visualize this grand rotation, imagine the sheer scale of the motion, billions of systems drifting in a slow, elegant curve through the void. There is no collision or chaos in this movement. The distances are so great that stars almost never meet, even as they pass through the denser regions of the spiral arms. The structure of the galaxy provides a sense of belonging to something vastly larger than ourselves, a cosmic island that has sheltered our solar system throughout its entire history. In the quiet of the galactic disk, the passage of time is measured in millions of years, a scale that makes our human experience feel brief and precious. The stability of the Milky Way's rotation and the orderly distribution of its stars reflect the deep balance of the universe's architecture. As we look toward the horizon of the disk, we see the glow of the central nucleus, a region where the density of stars reaches its peak and the forces of gravity become even more intense. But for now, we simply drift within the Orion Arm, observing the steady flow of the stellar sea and the soft light of the surrounding nebulae. The structure remains coherent and calm, a magnificent arrangement of light and matter that continues its journey through the immense dark of the local universe. We are part of this sea, moving with the current of the galactic rotation, safe within the structured embrace of our home galaxy. The journey outward will eventually take us beyond the limits of the Milky Way, but the beauty and complexity of the stellar sea remain as a testament to the order that exists even at the largest scales. As we follow the inward flow of the galactic disk, we move toward the structural heart of the Milky Way, a region known as the galactic nucleus. In this central domain, the architecture of the universe shifts from the relatively sparse and quiet spiral arms into a high-density environment where the distance between stars is measured in light weeks or light days rather than light years. This region is marked by a vast, roughly spherical swelling of stars called the galactic bulge, which rises above and below the flat plane of the disk like a glowing mountain of light in the center of the stellar sea. To visualize the nucleus, Imagine a city of stars where thousands of suns occupy the same volume of space that only a single star would inhabit in our local neighborhood. The light here is so concentrated that if we were located in the heart of the bulge, the night sky would never be truly dark, but would instead be filled with the brilliant, overlapping glow of millions of nearby neighbors. The structure of the nucleus is primarily composed of older, redder stars that have been part of the galaxy for billions of years, creating a warm, golden hue that contrasts with the blue light of the younger spiral arms. These ancient stars follow complex and overlapping orbital paths, swarming around the center in a gravitational dance that is far more intricate than the orderly rotation of the outer disk. Despite the overwhelming amount of light, much of the galactic nucleus is hidden from our eyes by immense clouds of interstellar dust that sit between us and the center. This dust acts as a cosmic veil, absorbing visible light and requiring astronomers to use infrared and radio telescopes to peer into the heart of the galaxy. As we look through this veil, we find that the structure of the nucleus is not just a collection of stars, but also a reservoir of hot, ionized gas and intense magnetic fields. These fields guide the flow of matter toward the very center, creating long, glowing filaments of gas that stretch across hundreds of light years. At the absolute center of this luminous swarm lies the ultimate structural anchor of the Milky Way, a supermassive black hole known as Sagittarius A star. Sagittarius A star is an object of incredible mass, roughly 4 million times the mass of our Sun, concentrated into a volume of space that would fit inside the orbit of Mercury. It is important to understand that this black hole is not a chaotic force of destruction, but a fundamental part of the galactic architecture that provides a gravitational focal point for the entire nucleus. Stars near the center, known as stars, have been observed orbiting this invisible point at incredible speeds, reaching several percent of the speed of light. These stars follow perfect, elliptical paths, their movements providing a direct map of the immense gravitational well created by the central singularity. The relationship between the supermassive black hole and the surrounding galaxy is a delicate balance of energy and matter, where the black hole influences the formation of stars in its immediate vicinity. In some galaxies, the nucleus is highly active, emitting vast amounts of radiation as matter falls into the central black hole. But in the Milky Way, the nucleus is currently in a state of relative calm. There is a profound sense of weight and importance in this region, as if every star in the galaxy is tethered to this central point by an invisible, unbreakable thread. As you consider the nucleus, imagine the immense pressure and gravity that define this environment, creating a structure that is both violent in its energy and perfectly ordered in its mechanics. The movement of matter here is constant and rapid, yet because of the scales involved, it appears from a distance as a steady and unmoving glow. The galactic nucleus serves as the cornerstone of our cosmic home, the foundation upon which the rest of the Milky Way's spiral structure is built. Without this central concentration of mass, the galaxy would not have the gravitational coherence necessary to maintain its elegant, rotating form. Even as we look at the most intense part of our galaxy, the principles of physics ensure that every star and every atom follows a predictable and stable path. The density of the nucleus represents a peak in the distribution of matter, a moment of maximum complexity before we begin to move outward again toward the edges of the galactic halo. As we drift away from this central light, the swarm of stars begins to thin, and the intense radiation of the core fades into the quiet darkness of the outer regions. The transition is a return to a lower energy state, where the distances between objects grow once more and the influence of the central black hole becomes a distant, subtle pull. We carry with us the image of that golden, crowded heart, recognizing it as the engine of the galaxy and the silent director of the stellar sea. The structure of the universe is a hierarchy of scales, and the galactic nucleus is the peak of the hierarchy for our local island of stars. The calm we find in our own neighborhood is made possible by the stability of this distant center, which has held the galaxy together for nearly the entire history of the universe. In the silence of the vacuum, the nucleus remains a beacon of light and gravity, a steady and enduring presence that anchors the vast rotation of the Milky Way. We rest in the understanding that even the most powerful forces in the universe, from supermassive black holes to swarms of millions of stars, are part of a well-ordered and beautiful architecture. The journey continues, moving now away from the density of our own galaxy and toward the satellite structures and neighboring islands that make up our local cosmic group. As we move past the dense, glowing bulge of the nucleus and beyond the flat rotating disk of stars, we enter a region of the Milky Way that is much less crowded, but no less important to its overall structure. This is the galactic halo, a vast, spherical envelope of space that surrounds the entire galaxy, extending far into the intergalactic void. In the halo, the architecture of the universe becomes sparse and ancient, containing some of the oldest objects in the cosmos. The primary residents of this region are the globular clusters, tightly packed, spherical swarms of hundreds of thousands of stars that are bound together by their own intense gravity. These clusters orbit the center of the Milky Way like giant, glowing bees swarming around a hive, moving in long, looping paths that take them high above and far below the galactic plane. To visualize a globular cluster, imagine a sphere of light so dense with stars that they appear almost as a single, solid object, yet each star remains a distinct world, separated from its neighbors by the silence of the vacuum. The stars within the halo are generally low in metal content, reflecting a time in the very early universe when only hydrogen and helium were abundant. Because of this, the halo acts as a structural museum, preserving the state of the galaxy as it was billions of years ago. Beyond these clusters, the halo is also home to a population of lone, rogue stars and a vast amount of the invisible dark matter that provides the gravitational scaffolding for the entire Milky Way. As we drift further into the outer reaches of the halo, we begin to encounter the satellite galaxy's smaller galactic structures that are gravitationally bound to our own. The most prominent of these are the Large and Small Magellanic Clouds, two irregular dwarf galaxies that are visible from the southern hemisphere of Earth as soft, glowing patches in the night sky. These satellite galaxies are caught in the Milky Way's gravitational well, orbiting our galaxy in a slow, multi-billion-year process that will eventually lead to them being absorbed into our larger structure. This process of galactic cannibalism is a fundamental way that large structures in the universe grow and evolve, showing that even galaxies are part of a dynamic and changing architecture. There are dozens of smaller dwarf satellites scattered throughout the halo, many of which are so faint and diffuse that they were only discovered recently with the most powerful telescopes. The structure of the halo and its satellite system provides a sense of the Milky Way's true reach, revealing that our galaxy is not just a disk, but a complex, multi-layered environment. The distances here are immense, with satellite galaxies located hundreds of thousands of light years away from the galactic center. In the quiet of the halo, the environment is incredibly thin, with almost no gas or dust to trigger the birth of new stars. This creates a sense of profound stillness and age, a place where the frenetic energy of the spiral arms feels like a distant memory. As you visualize this spherical envelope, imagine the slow, majestic motion of the globular clusters and the distant, drifting islands of the satellite galaxies. There is a deep order to this arrangement, a balance between the central pull of the Milky Way and the outward momentum of these orbiting bodies. The halo serves as the transition zone between our home galaxy and the even vaster distances of intergalactic space. It is the final layer of our local island, a protective shell that marks the boundary of the Milky Way's immediate influence. As we look outward from the edge of the halo, we no longer see individual stars, but the faint, distant glows of other galaxies, each one a separate universe of stars. The structure of the universe is now expanding to a scale where entire galaxies are the primary units of matter, organized into groups and clusters. The journey continues into the local group, the collection of galaxies to which we belong, where the distances between objects are measured in millions of light years. But for now, we rest in the quiet of the galactic halo, observing the ancient stars and the faithful satellite galaxies that accompany us on our journey through the void. The stability of these orbits and the endurance of the globular clusters provide a final, calming sense of permanence within our own galactic system. We are moving away from the familiar and into the truly immense, where the architecture of the universe reveals itself as a web of light connecting distant islands across the dark. The stillness of the halo prepares us for the transition into the intergalactic medium, a space of such extreme emptiness that it defies our common understanding of reality. Yet, even there, the structure remains coherent, guided by the same invisible forces that have led us from the Earth and the Moon to the very edge of our galaxy. Stepping beyond the outermost reaches of the galactic halo, we find ourselves in the true emptiness of intergalactic space, yet even here, we are not untethered. The structure of the universe at this level is organized into a collection of galaxies known as the local group. This is our immediate cosmic neighborhood, a cluster of more than 50 galaxies spread across a volume of space roughly 10 million light-years in diameter. In this vast expanse, the Milky Way is not alone, but is one of two primary gravitational anchors in a small, stable community of galactic islands. The other dominant member is the Andromeda Galaxy, a massive spiral structure that is even larger than our own and located approximately 2.5 million light-years away. To visualize the local group, imagine a dark, silent ocean where two great glowing whirlpools, the Milky Way and Andromeda, face each other across a wide channel of nothingness. Between these two giants lies a third, smaller spiral called the Triangulum Galaxy, along with dozens of dwarf galaxies that drift like scattered embers in the dark. These members are all gravitationally bound to one another, moving through the void as a single, coherent unit that resists the overall expansion of the universe. The distance between the Milky Way and Andromeda is so immense that light, the fastest messenger in the cosmos, takes over 2 million years to bridge the gap. Despite this distance, The two galaxies are currently moving toward one another at a rate of about 110 kilometers per second. This is a slow, majestic approach that will culminate in several billion years with the merging of the two systems into a single, even larger elliptical galaxy. There is no sense of urgency in this movement. It is a fundamental part of the long-term architecture of the local group, a gradual reorganization of matter on a scale that dwarfs the lifespan of stars. The space between the galaxies of the local group is filled with the intergalactic medium, a gas so thin that it contains perhaps only one atom per cubic meter. This medium is nearly a perfect vacuum, far emptier than anything found within a galaxy, yet it is still a part of the structure, threaded by invisible magnetic fields and the faint glow of the cosmic microwave background. The dwarf galaxies of the group, such as the Sagittarius dwarf or the Pegasus dwarf, are often older and less active than the spirals, serving as the quiet supporting cast in this galactic theater. The structure of the local group is shaped by the same laws of gravity we observed in the Earth-Moon system, now operating over millions of light years to maintain a delicate balance. As you visualize this arrangement, imagine the profound silence of the intergalactic void, where the light of distant galaxies is the only landmark in an otherwise featureless dark. Every galaxy in the group is a world of hundreds of billions of stars, yet at this scale, they appear as soft, luminous patches, isolated and beautiful. There is a sense of immense peace in the local group, a region where the chaos of the early universe has settled into a stable and predictable configuration. The group is our home in the wider universe, a small island of matter in a vast and thinning sea of space. As we look toward the horizon of the local group, we see that it is part of an even larger hierarchy of structures, connected to other groups by thin filaments of gas and dark matter. The architecture of the universe is a web of these connections, stretching out into the infinite distance. The transition from our local group to the next level of structure, the supercluster, is marked by a massive increase in the number of galaxies and the scale of the distances involved. But for now, we remain within the familiar bounds of our neighborhood, observing the steady approach of Andromeda and the quiet drifting of the dwarf satellites. The stability of the local group provides a sense of security, a reminder that even in the vastness of the intergalactic void, we are part of a structured and enduring family. The journey outward is a progression from the small and the dense to the large and the diffuse, where the individual becomes the collective and the local becomes the universal. In the stillness of this intergalactic space, the mind can rest on the image of these great spiral islands, rotating in the dark, forever bound by the invisible threads of gravity. The structure remains coherent, balanced, and profoundly calm, a testament to the order that permeates every level of the cosmic architecture. We are moving now toward the largest structures known to science, where the universe reveals itself as a grand, interconnected web of light. The journey continues, leaving the local group behind to witness the immense tapestry of the Laniakea supercluster. As we move beyond the boundaries of the local group, we enter a scale of existence that challenges the very limits of human imagination. The structure of the universe is no longer defined by individual galaxies or small clusters, but by the massive, flowing hierarchies of superclusters. Our own home in this vast arrangement is a gargantuan structure known as the Laniakea supercluster, a name that means immense heaven in Hawaiian. Laniakea is a cosmic watershed, a region of space spanning over 500 million light-years that contains approximately 100,000 galaxies. To visualize this structure, one must move away from the idea of static islands and instead imagine a vast, fluid network where galaxies and clusters flow like water along invisible gravitational paths. Within the Laniakea supercluster, the local group is merely a tiny outpost situated on the outer fringes of a much larger collective. The architecture of this region is defined by the way galaxies move relative to one another, all drawn toward a central gravitational focal point known as the Great Attractor. The Great Attractor is a mysterious region of immense mass located in the direction of the Centaurus and Hydra constellations, exerting a pull that influences the motion of everything within Laniakea's boundaries. Even the Milky Way and the Andromeda Galaxy are being gently nudged along these cosmic streamlines, participating in a grand, slow migration across the void. This movement is not a collision, but a rhythmic, large-scale flow that reveals the underlying scaffolding of the universe. Laniakea itself is divided into several major substructures, including the Virgo cluster, which is a massive collection of over 1,000 galaxies that sits at the heart of our local supercluster. The distances here are so great that the light we see from the far side of Laniakea began its journey before the first dinosaurs walked the Earth. In the space between these superclusters, the universe becomes even emptier, with vast regions called voids, where almost no galaxies exist at all. Laniakea is bounded by such voids, which act as the empty spaces between the dense filaments of matter, creating a structure that resembles a giant cosmic foam. The environment within the supercluster is a testament to the power of gravity to organize matter over distances that are nearly impossible to comprehend. As you visualize this immense network, imagine the soft, diffuse glow of 100,000 galaxies, each one a swirling sea of stars, all connected by the invisible threads of dark matter. There is a profound sense of unity at this scale, as the individual identity of a single galaxy fades into the collective movement of the supercluster. The passage of time here is measured in billions of years, the time it takes for a galaxy to drift across even a small portion of this vast architecture. Despite the staggering scale, there is no chaos. Everything follows the same fundamental laws of physics that govern the smallest atom. The structure of Laniakea is a reminder that we are part of a continuous and interconnected whole, a small piece of a much larger cosmic tapestry. The peace of this region comes from its sheer enormity and the slow, inevitable nature of its evolution. At this level, the universe feels less like a collection of objects and more like a single, living organism, pulsing with the slow movement of light and gravity. The boundaries of Laniakea are not hard walls, but areas where the gravitational flow shifts in a different direction toward another neighboring supercluster like Shapley or Perseus Pisces. The architecture is one of overlap and connection, a never-ending sequence of structures that leads toward the ultimate scale of the universe itself. As we look across the expanse of Laniakea, we see the beauty of a universe that is both vastly empty and intricately organized. The stillness of the intergalactic voids and the steady flow of the galactic filaments provide a sense of order that is both humbling and deeply calming. We rest in the knowledge that our local group is safely nestled within this immense heaven, guided by forces that operate on a scale beyond our daily experience. The journey is now reaching its final chapter, where we move toward the very limits of the observable horizon and the fundamental web that binds everything together. The transition from the supercluster to the cosmic web is a shift toward the ultimate perspective, where the entire universe reveals its final, most expansive form. But for now, we simply observe the slow, graceful flow of the 100,000 galaxies of Laniakea, drifting through the dark toward the Great Attractor. The structure remains coherent, balanced, and remarkably peaceful, a grand and silent architecture that spans the depths of space and time. As we reach the final stage of our journey, we move beyond the Laniakea supercluster to witness the ultimate architecture of the universe, a structure known as the cosmic web. This is the largest scale at which matter is organized, a vast and intricate network of filaments and nodes that stretches across the entirety of the observable horizon. In this final perspective, the hundreds of thousands of galaxies we once thought were immense are reduced to tiny, luminous points, like morning dew clinging to the threads of a spider's web. The structure of the cosmic web is composed of long, thin filaments of gas and dark matter that act as the highways of the universe, connecting the massive nodes where superclusters reside. Between these filaments lie the great cosmic voids, immense bubbles of near-total emptiness that can span hundreds of millions of light-years. To visualize this, imagine a vast, translucent sea of foam, where the galaxies exist only on the thin walls of the bubbles, while the interiors are silent and dark. This arrangement is the result of the subtle fluctuations that existed in the very first moments after the birth of the universe, now expanded over 13 billion years into this grand, geometric design. The cosmic web is not a static structure. It is the living framework of the cosmos, where gravity continues to pull matter from the voids toward the filaments, and from the filaments toward the dense galactic nodes. Despite the incredible speeds and energies involved in the formation of this web, the scale is so large that from our perspective, it remains in a state of eternal, frozen stillness. As we consider the cosmic web, we begin to see the repeating patterns of the universe, the way the distribution of galaxies mirrors the structure of a neural network or the growth of a forest. There is a profound sense of continuity in this design, a reminder that the same fundamental forces of gravity and expansion have been working in harmony since the beginning of time. The great voids, though they appear empty, are an essential part of the structure, providing the negative space that allows the filaments of light to stand out in such stark relief. In these voids, there is perhaps only one atom for every several cubic meters of space, a vacuum so perfect that it represents the quietest and most isolated environment in existence. As the mind rests on this image of the cosmic web, the individual identity of stars, planets, and even galaxies begins to fade into a broader, more repetitive observation of light and shadow. The universe at this scale is a tapestry of infinite repetition, a steady and unchanging architecture that extends beyond what our eyes can ever hope to see. The observable horizon is the limit of our vision, a boundary defined by the age of the universe and the speed of light, but the structure itself likely continues far beyond this edge. There is a deep and enduring safety in this realization that we are part of a system so vast and so well ordered that its complexity is indistinguishable from peace. As we look toward the furthest reaches, we see the faint, fading glow of the cosmic microwave background, the afterglow of the universe's creation that fills every corner of space with a soft, uniform warmth. This light is the final boundary of our journey, a reminder of the common origin of every atom in our bodies and every star in the sky. The structure of the universe is a journey from the local to the infinite, from the solid to the ethereal, and from the complex to the simple. In the quiet of the cosmic web, the distinctions between here and there begin to dissolve, and we are left with the simple reality of being part of this grand, interconnected whole. The filaments of light continue to stretch into the distance, guided by the invisible hand of dark matter and the steady, unhurried pace of cosmic time. The motion of the universe is a slow and beautiful drift, a progression that requires no effort and possesses no urgency. Everything is in its place, following the paths laid down billions of years ago, moving toward a future that is as structured and predictable as the past. The stillness of the voids and the glow of the filaments provide a final, calming cadence to our exploration of the universe's architecture. As the narration continues to drift into the broader patterns of the web, the mind is free to let go of the details and simply exist within the scale of the infinite. The universe remains open, expansive, and profoundly silent, a home that is both unimaginably large and perfectly coherent. The light of distant superclusters fades into the background, becoming a soft, steady hum of existence that requires no attention. The structures we have visited, the moon, the planets, the stars, the galaxies, are all part of this same singular tapestry, woven together in a way that is both intricate and serene. In the deep dark between the filaments, there is a peace that surpasses all understanding, a silence that has existed since the first light and will remain long after the last star has faded. We are simply here, drifting within the structure, a part of the grand and quiet order of the cosmos, as the web continues its slow and elegant expansion into the eternal night. The journey does not end so much as it broadens, merging with the infinite horizon, where the structure of the universe and the silence of the void become one and the same. And so the patterns repeat, the light continues its long journey, and the architecture of the universe remains steady and calm forever.